Let's take a look at the criteria for aromaticity. How do we decide if a molecule is aromatic? We have several rules that it must follow. The first is that it must be in a ring, so we must have atoms in a ring. We must have continuously overlapping p orbitals in that ring, so we cannot have any sp3 hybridized carbons or other atoms. And it must be planar. So if our ring is large enough and it can flex and become non-planar, these p orbitals are no longer continuously overlapping. So the ring must be planar as well as having the continuously overlapping p orbitals. They also must follow the Huckel number, which means that the number of pi electrons must be 4n plus 2. Thus, the allowed numbers of pi electrons would be 2 if n equals 0, 6 if n equals 1, 10 if n equals 2, 14 if n equals 3. You get the idea. So we must have one of those numbers of pi electrons. Let's look at some of these examples in blue. Hexatriene obviously does have the Huckel number of pi electrons. It has 6. However, it's pretty obvious right off the bat, this is not a ring. So this is not an aromatic compound. So we can call it non-aromatic or simply not aromatic. Let's look at the next compound. This is Cyclopentadienyl, and it is in a ring. It does have some p orbitals, but this carbon right here at the top is sp3. And so if it helps you to add some hydrogens there, feel free to do that. This is an sp3 carbon, so it does not fit our rule of continuously overlapping p orbitals. So this is also non-aromatic. The next one, cyclooctatetraene, this is trying to be an 8-membered ring with 4 alternating pi bonds. And you can see that the way I drew it, it is actually not a planar ring, and this is true. Scientists have studied cyclooctatetraene and discovered that it is not a planar system of 8 carbons in a ring. And one reason is because if you count the pi electrons, you'll come up with 2, 4, 6, 8, which is not a Huckel number. It is in fact a 4n number, which lends itself to anti-aromaticity, which is even worse than simply not being aromatic. Anti-aromatic compounds are actually much higher in energy than if they were simply non-aromatic compounds. After all, we've dealt with many non-aromatic compounds on paper, in class, and in the laboratory over the past semester and a half. So those really don't have a problem. They don't have this special stability that is achieved by being aromatic. But if we discover a molecule that is anti-aromatic, which means it's a ring, it's got p orbitals, it's planar, and yet it has 4n pi electrons, which is 4, 8, 12, it's actually anti-aromatic and even worse off than if it were non-aromatic. So this molecule, cyclooctatetraene, adopts a non-planar configuration so that it can avoid being anti-aromatic. So this is non-planar, and that means it's non-aromatic, which isn't really a problem. It just doesn't have the extra stability that an aromatic ring does. And looking at this last one, we've seen benzene many times the first semester and now in the second semester. This is a ring. This does have continuously overlapping p orbitals. It is planar, and certainly the number of pi electrons does equal 4n plus 2 when n equals 1. We know that there are 6 here. So this is aromatic. And we know that it has some extra stabilization in benzene compared to hexatriene, which is a very similar compound in terms of the HDI and the number of pi bonds. It's just that it's not in a ring, and we don't get that aromatic setup. Let's look at a couple other examples here. This is cyclopentadienyl with a cation in the place of that CH2 that we saw a few seconds ago. And so this molecule does have a continuously overlapping set of p orbitals. It is planar, it is in a ring, but it only has 4 pi electrons. Therefore, it fits the anti-Huckel rule, the anti-aromatic number of electrons. Remember that I said if everything else is equal, planar, cyclic structure, and it has p orbitals all around, and we know that this is an sp2 type carbon up here because it is a cation. We know that it's planar. And so this is anti-aromatic, which means that a chemist probably will have difficulty even forming this in the laboratory from cyclopentadienyl. In fact, this probably reacts very quickly with anything in order to maybe rehybridize this carbon to sp3 such that we don't have that continuously overlapping ring of p orbitals anymore, and thus that would change it to non-aromatic, which is a much more favorable state than an anti-aromatic. So this compound is probably rather hard to form. Let's compare that with the anion version of this compound. What do you think about that? It is in a ring. If this carbon hybridizes such that this this lone pair is in a p orbital, we have a continuously overlapping ring of p orbitals, and certainly 5 carbons in a ring could be planar. And if I count this in my pi electron count, 2, 4, 6, I get 6 electrons. This is aromatic. And what this tells me is that cyclopentadienyl, which, let's draw that again just for refresh your memory, cyclopentadienyl is probably very acidic at this position, because if I remove one of the protons there, leaving behind the lone pair, I achieve this state, which is an aromatic anion. So this cyclopentadienyl is actually a very acidic compound, more than we'd expect, because this is a CH that we're dealing with in terms of acidity. Once we've deprotonated that H here, we gain an aromatic compound. Let's look at the cyclopropylenyl anion. I think you'll agree it is in a ring. If this anion is a lone pair in a p orbital, we have a continuously overlapping p orbitals. This is planar. 3 points make a plane after all. But we have 4 pi electrons here. This is anti-aromatic. Therefore, very hard to form. Probably not going to form. Looking at the other option here, cyclopropylenyl cation. Here we only have 2 pi electrons. All else is the same. A ring, p orbitals, planar. We only have 2 pi electrons. This is aromatic. Which means that if I had this compound, that might be rather likely to lose this chloride as a leaving group, because the resulting cation right here is aromatic. So this chloride is probably a very labile, very easily lost leaving group compared with, say, this chloride, which would not leave behind a aromatic compound. So if we lose this chloride, we get an aromatic carbocation. If we lose this chloride, we do not. And so this probably is a very much more reactive species in terms of alkyl chlorides. One more, let's look at this one. It's called Pyrrole. It is a 5-membered nitrogen-containing ring, so we have a heteroatom in here. Makes it a little more exciting than the standard carbon rings. And we can count 5 atoms in the ring. We can assume they're all planar. The nitrogen, if it rehybridizes to put this lone pair in a p orbital, we will get a continuous overlapping set of p orbitals. That makes sense. That would be favorable in terms of the aromaticity. And so the nitrogen does rehybridize. Chemists have studied that. And we know that that lone pair is in a p orbital. Thus, we have an aromatic compound, because that lone pair would give us the 6th pi electrons. So this Pyrrole is aromatic. And that means that the lone pair is not basic. It is involved in aromaticity. The molecule is not going to want to give up that lone pair in terms of the nitrogen being a base, right, making another NH bond right here using the lone pair. If that were the case, we would get something like this. And you can see that we've lost that lone pair. We've lost our continuous overlapping set of p orbitals, right? This nitrogen is now sp3 hybridized. There's no way around that. And so we've lost the aromaticity. So this is not a very basic lone pair. We cannot use that as a base. A couple more examples. Looking at this oxygen-containing heterocycle, a ring with a heteroatom in it, we can quickly observe that these 2 carbons do not have p orbitals. They are sp3 hybridized, therefore we do not have the ring of p orbitals, therefore this would just be non-aromatic. And if you're answering a question like this on the exam, I probably would like you to label it aromatic, non-aromatic, or anti-aromatic, and tell me why. So you can't just label it and leave it like that. Looking at this molecule, this is called furan. It has an oxygen. I think there are 2 lone pairs on there. Let's draw those in. That will be helpful to us. If the oxygen were to rehybridize and put one of those lone pairs in a p orbital, we could then have our ring of p orbitals, and we could have 1 lone pair, 2nd lone pair, 3rd lone pair, 6 pi electrons. This could be aromatic. And so if that is the case, the molecule generally, nature will generally say this oxygen has rehybridized into sp2 plus p. And we can confirm that by looking at the molecule using certain spectroscopic techniques. We'll find that the oxygen has adopted the bond angles and the planarity that we would expect of an sp2 hybridized atom. Let's look at this molecule. We've got a pendant amino group here, and we've got a ring of p orbitals. Don't let this distract you. It doesn't matter what are on the outside of this ring. I could add a couple more methyl groups if I wanted to, or an isopropyl group. That's not going to affect necessarily the planar structure of this ring, nor the fact there are 6 continuously overlapping p orbitals. This nitrogen is sp2 plus p. We know that because it is participating in a pi bond with the adjacent carbon. So we have p orbitals all around. We've got, let's count the pi bonds, 1, 2, 3. We've got 6 pi electrons. So it does fit the aromatic nature. You may ask me about this this lone pair up here, but if we look at this nitrogen, that's an sp2 orbital. There are sp2 orbitals being used to bond to the adjacent carbons, and then of course the p orbital, which I'll try to sort of draw in red, projecting out of the screen and below the screen. That p orbital is being used to make this pi bond here. And so this lone pair has to be in an sp2 orbital, which puts it in the plane of the ring, outside the ring. It is not participating in the pi bonding. It does not count in terms of the Huckel number. So we don't count this lone pair when counting the Huckel number. Just like we don't count this lone pair because it's outside the ring. It doesn't matter what's going on over here. That has no bearing on the Huckel number. So we have 6 pi electrons here. This is not considered a set of pi electrons. And so this molecule would be aromatic as well. And if we're going to talk about the basicity of this lone pair, here's an example of a nitrogen lone pair that is basic because it's not participating in the resonance and the aromaticity. So let me try to draw a line here. This lone pair is basic, and this molecule is very close resemblance to pyridine, which has that nitrogen in the 6-membered ring with a basic lone pair. And so we can use that lone pair as a base. It does not affect the aromaticity. The molecule remains aromatic even after protonating that lone pair.